Hello there. We're going to look at further distances today. So how do we figure out how far away a star is if it's really far away? We learned in the last lesson that we can use the parallax method to figure out how far away a star is if it's quite close. Because what we do is we look at it where it is now, we look at it 6 months later when we're on the other side of the sun, so our position has shifted a little bit, and just like closing one eye and opening the other and then swapping over, you would notice that there's a slight shift compared to the background of distant stars. So we're comparing close-up stars and how they appear to shift against the background of distant stars. But if the distant stars are our context, then how do we figure out how far away they are? So the parallax method would only allow us to figure out the distance to things that are close to us. So we need to learn how to figure out how far away the distant things are. Okay, so this tries to make a point about the problems that we face. This is a well-known optical illusion, and the two rectangles are the same size, but your brain often tells you that the further one is bigger. So what you do when you look at things on Earth is you place it into the context of its surroundings. But in space, astronomy, we're looking at a dot of light against the black background. So there's no context to put it in. So we have no way or normal means of figuring out how far away it is. Actually, your eyes use parallax, so your left eye and your right eye work together to, and they've got slightly different images. And by how different those two images are, your brain processes that and works out how far away the object is. So it's quite hard to get depth perception with just one eye. So here's the equation. This equation links three things. Capital M, which is absolute magnitude. Lowercase m, which is apparent magnitude. And d, which is distance measured in parsecs. Now, to use any formula, to work out anything in any formula, you can only have one unknown. If you have two unknowns, all you could work out is a ratio. Or you might come up with a clever way of combining it with another formula, equating, cancelling out. But essentially, you need to work out everything. You need to know everything except one thing, and then you can work out that last thing. Now, the absolute magnitude is the thing that we'd like to know, as well as distance, I would say. Apparent magnitude is easy. It's based on the Hipparcos scale, 1 to 6, and we just place it on that scale. So it's how bright it appears from Earth. So we can get that whenever we want. And distance, we could use the parallax method to figure out the distance. So once we know the distance and we know the apparent magnitude, we can figure out the absolute magnitude of a star. But the parallax method only works for close-up stars. What if it's too far away? The parallax method cannot be used. So therefore, we have two unknowns, absolute magnitude and distance. So we were stuck. We couldn't work out the distance to the faraway stars. And then came Henrietta Swan Leavitt. So there'll be a little video linked to this on Henrietta Swan Leavitt, but she gave us the ability to figure out how far away very distant galaxies were by observing things called variable stars. She first observed them in the constellation Cepheid, so they're known as Cepheid variable stars. Henrietta Swan Leavitt was doing a job which would have been known as a computer. She was analysing data for other astronomers, but in her spare time she did some research herself into these variable stars which she'd noticed, and she noticed a very important link between two things. So this is a Cepheid variable star, and you can see that area of that galaxy has been magnified, and the first image compared to the second compared to the third, you can see it gradually gets brighter. So what's happening with these variable stars is they swell up and then they shrink back down again. And she noticed a link between the brightness of the variable star, which we've said it gets brighter and then dimmer, and how long it takes to do that. So you can see that there's a sudden peak in brightness. It's very dim, and then it suddenly gets brighter, and then gradually over time it gets dimmer. And then it suddenly gets brighter again, and gradually over time it gets dimmer. Now, you might be thinking that the magnitude scale is a negative scale, but the way this graph is done, it's probably more a graph of luminosity or you could just think of it as having a negative axis for a negative scale. So the higher it goes, the brighter it gets. And she found that there was a link between how bright a star actually is and how long it takes to get brighter, dimmer and brighter again. So that's the period, or the time period, of a variable star. So the time period is how long between peaks of brightness. And she found that the brighter the star was, the longer the time period was. So dim stars go bright, dim, bright again. But your bigger stars, your brighter stars, they will go bright. Over a long period of time they'll go dimmer, and then they'll get brighter again gradually. Okay, so the smaller stars have a smaller time period. And that was important, because when all she needed to do was measure the time period of the Cepheid variable star, and then she could link it on this graph and find out what its absolute magnitude was. So that would become something of known magnitude. Once it was observed and timed, it's often in days, weeks, how long it takes for the time period to elapse, then she would be able to just plot it on this graph, as I said, and we then know how bright that star is. And don't forget, we would also be able to work out the apparent magnitude. So if we know big M and we know little m, then we just need to use that equation to work out D. So Henrietta Swan Leavitt had given us a way to observe variable stars and then work out how far away that star was. And if that was in a particular galaxy, of course that tells us how far away that galaxy is. Okay, so that's the link. Never seen them ask you to sketch that graph. You might be given the graph on the left and be asked to explain it, or you could be asked just for 2 or 3 marks maybe to explain how we use variable stars as standard candles. I'll get to what a standard candle is in a second. But yeah, I would sketch them 2 graphs, important to understand. And the one on the right says the greater the time period, the greater the absolute magnitude of the star. The only thing that could throw you there is you might want to put luminosity, or how bright the star is, on that y-axis, because of course absolute magnitude is a negative scale. But you could just start 0 here, -5, -10, -15, and go up with that negative axis there. Okay, so certainly sketch those. Pause the video, sketch those graphs. So there's a phrase that I've mentioned, standard candles. And a standard candle is defined there, something in astronomy with a known luminosity. It's always the same brightness, or we know what the brightness is. So a Cepheid variable star is one of 2 examples of standard candles that you need to understand. So a standard candle could be a Cepheid variable star, but there's another thing that we would observe in astronomy that we would use as standard candles, which is a type of supernova as well. Okay, now a standard candle is if you think about candles before candle shops and scented candles were popular gifts, you would buy candles in hardware stores, DIY stores, and they'd just be a long, thin, white candle. So all candles would have been about the same brightness, and so comparable. So if you had a dark background and you knew somebody on that background, so a massive field where you couldn't see anything other than somebody holding a candle, just the candle that he held, you could probably figure out how far away that candle was by how bright it appeared, because you know actually how bright it is. So if it's really dim, you'd know it's really far away. So that's kind of the essence of what we're using. If you know how bright something is, and you know how bright it looks, you can work out how far away it is. So that then gave us the ability to work out M, big M. Oh, that's a dodgy looking arrow there. So once we'd worked out big M from the period luminosity law, that should be pointing there. Then we know big M, we know little m from simple observation, so then we can calculate D. Okay, so Henrietta Swan Leavitt gave us the way to calculate D for distant stars. Now, this is an example of the second type of variable star. What you'll see is certain stars, when they die, the larger stars, they'll go supernova. And a supernova is a huge explosion and release of energy. It's the most energetic thing you can observe in the universe, and it's where all the heavier elements are made, and it's only the heavier stars that will go supernova. And you'll be observing a galaxy, and this galaxy, apologies, this galaxy was, just suddenly had this huge increase in magnitude and be observed. And you can observe supernovas most nights, if you've got the right equipment. So it's happening all over the universe. Really easy to find now by the astronomers. And if something close to us goes supernova, then you will notice it. It's like a second sun in the sky. You have records of people observing this in the 11th century, and we've got Betelgeuse close to us, which could go really at any time. And then for a few weeks, you'd have like something really bright in the sky, as well as the sun and the moon, which would be exciting, really, and concerning for people who suddenly spotted it, I suppose. But supernovas come in different types. There's different types of supernovae. There's different ways that a star can explode, and there's a certain supernova called Type 1a supernova. So this is just showing where it was. But Type 1a supernova always have this graph. So what you do is you'd spot a supernova, something like that, suddenly appearing in a galaxy, and it would gradually be increasing its luminosity. So you would observe it, and you'd plot it on a graph, and then if it started to plot out this exact shape, then you would know that it's a Type 1a supernova. Now, Type 1a supernovae always have the same magnitude of maximum brightness. So you could observe it. If you see the right shape, then it's a Type 1a supernova. So that means that you know its maximum brightness, or its absolute magnitude there. The time that it's measured from starts when it reaches its peak. They put that as 0. Okay, and you can see it typically lasts a few months there. So if we know its absolute magnitude, again, it works exactly the same as before. We use that, we find a Type 1a supernova, we know its absolute magnitude, we measure its apparent magnitude from simple observation, and then you put it into that formula to calculate distance measured in parsecs. And all you need to do, so therefore, is find either a Type 1a supernova in a galaxy or a Cepheid variable star in a galaxy, and that tells you the distance to the galaxies. Okay, now, this work was used by Hubble. So the Henrietta Swan-Leavitt's period luminosity law was used along with the equation with little m, big M and D in to calculate the distance to galaxies by Edwin Hubble. He also used work on the Doppler shift and the Doppler effect and redshift to figure out how much redshift they showed. So he linked how much redshift something shows with how far away it is, and then he came up with the theory of the Big Bang, which is something that we'll have to study as well. But it was without the work of Henrietta Swan-Leavitt, a huge amount of follow-on work wouldn't have been possible. And as I've said, it was amazing that she just did it kind of in her spare time while working for the astronomers in such a time where it would have been much harder for a woman to break through into that field. So unbelievable work by her, and the amount of people that benefited was huge. So there was a trickle of breakthroughs shortly after that, and the universe suddenly became understandable as this vast thing compared to the much smaller idea that people had of the universe before them. So other than this, there's a video to support this, and then I suppose there's notes to make on Cepheid variable stars and Type 1a supernovae, and that'll be it for here. So I hope that was helpful. Thank you very much.